read that correctly. That's amazing.
Awesome.
I had a quick question too, really quick. I was just wondering if the grade that goes on my lab is the grade that's going to be entered on Canvas.
Yes, that's correct. What I'm pretty much going to do is go into the MyLab homework system. And let me close this for a moment. Once the very first due date gets past due, I'm going to go here and just post what grade I see there directly onto the Canvas system. And so your actual grade from right here is going to show us a percentage. That's going to be the percent you have on just this part right here, the percent grade on the homework side in MyLab. Other questions at the moment? Welcome back, folks. Okay, well, we got back from the holiday. I hope you all had a great Martin Luther King Jr. holiday. We'll have another one in February for President's Day. It's kind of weird to do a week, then take a day off, and then get right back into it. So far, we're on example 12 on the Unit 2A notes. And the other big thing going on is we mentioned we're also going to have weekly quizzes, and the very first quiz is posted. Usually what I want to do is consider these as officially posted on Thursday, but Thursday is my busiest day. I teach 3 classes, so it's hard to write a quiz, proofread it, get it posted all in time with the other things I have to do for my other classes. So I'm usually going to post them on Wednesday. They'll have a full 1 week turnaround, which is the 29th, since we're going to say it's officially posted on the 22nd, but I'll often be posting them just a day early just to make sure everything's placed here on time for Thursday's class. So we're going to be finishing off the Unit 2A notes soon. Notice also I put a due date on the section 2, Unit 2A, not the section, as well. And this is going to be a habit that I'm getting into. Once I know we're completing a particular unit on a given day, I'll post the due date, and that'll be the same due date that you'll see in MyLab as well. I want to also talk next a little bit about the quiz. If you want to start it early, that'll be just fine. But any questions so far? Okay, so as far as the homework side goes, here's where we'll probably spend a good amount of time reading the textbook, learning the material, and just doing the exercises that we see here. Quizzes worth 10% are going to be pretty short and sweet. So we won't spend necessarily as much time getting through the quizzes. Usually I'm going to ask essentially one problem, maybe 2 parts, a few parts, or something similar that we did in the lecture notes. And here's what it looks like for this particular quiz 1. If you click on the file or the link right here, it takes you to just a blank field with a file, a PDF file. And this is the problem that's considered assigned for quiz number 1. It's based on 10 points. And the way the grading works for the quizzes, I think I mentioned this on the first day of class, but it's been a while since then. 5 points are really just a participation credit. So that's part of the role the quizzes serve in this course is, for example, just the participation. So if you try it, put your name on it, turn it in, even if the work isn't correct, you're going to get a minimum at 5 points. The remaining 5 points are just for correctness on the work that you do on that quiz. Click on the PDF file here. The Canvas takes a minute to load this up. And here's what it looks like. You could download it and print it if you like. There'll be a problem similar to the ones that we did in the prior lecture notes. And this one's actually pretty similar from a problem that we have already done in Unit 2A. So this gives you a chance to actually write out the work, show your step-by-step solutions, and that way you'll get a feel for what would a real exam question actually look like, how would I write out the work, and how would it be graded as well. This kind of bridges the gap between the MyLab homework and the actual work you'll do in an exam setting. Well, any questions about the quiz at the moment?
So we can download it and then we can fill it out by hand and just like take a picture of it and then re-upload it.
Yeah, absolutely. Actually, there's going to be lots of ways that you could do this. I'm going to say it's really just up to the student preference. So Some people might just want to grab, say, an ordinary piece of paper. Here's some scratch paper with stuff filled in. If you grab an ordinary piece of lined notebook paper, work the problems down as you see it there, maybe label it part A, part B, part C, then that would be fine with me. You could take a picture of your work, upload it to Canvas, or send it to my ISU email address. Either way of turning it in is just fine, and that would be great. Other people might want to download it, print it out, work on it as a hard copy. Then, again, you could take a picture of it, either scan it or a cell phone picture is just fine. Send your completed work to my ISU email address, or you can directly upload it to Canvas, and that will work out as well. Still, other people might download it and start just working with digital tools like I've been doing on the course notes. You might fill it out, say Mike Jacobson, start working out the problems, just say the squiggly lines is my work to solve the problem, save your file, and then you can upload that back to Canvas or email it to me directly, and that'd be a third option. So really, there's no direct way that you have to work this. I don't have any major preference. As long as you're sending me in the work, I'll be happy to accept it. Does that make sense so far on how to send in the quiz work?
Yes, thank you.
Yep, absolutely. Other thing I mentioned on the day one when we were talking about quizzes, again, it's been a while, so it's easy to forget. We said a lot of stuff on day one. Let me backtrack this all the way back. Is that quizzes, they're just a way for you to get some additional work, a participation credit. That means they're not really quizzes in the traditional sense. They're like just an add-on to the homework, where the major homework is through here, Access Pearson in the MyLab. So the quizzes here, they're take-home quizzes. You can work these alone. You can work them in groups. You can even ask questions about them. You can ask me questions through email, through office hours, and you can ask people in the math lab, things like that, about the quiz, and that would be considered just fine. So really, it's just your way to get some work in. You can look into any of the work that we did here, the textbook, the lecture notes, and so on. Any tools that you would like to use to assist you getting through that quiz will be just fine. We'll remind ourselves about the quizzes when we come up to our Thursday's class, when it's considered officially assigned. And this is what the Canvas page is going to look like on a week-by-week basis. Each week we'll have new material, and at the very bottom, usually posted on a Wednesday, Thursday at the latest if I'm behind, will be just the very next quiz, which will be due with a 1-week turnaround. And I give a 1-week turnaround on the due dates for quizzes, only so that you have some chance to work in groups if you like, ask questions with me in office hours, and so on. My other objective with quizzes is to make them short because I don't want them to compete with the more work that I'll be spending in my lab doing the problem by problem. Well, I think that's pretty much it for the announcements that I had so far today. We're going to be returning to Unit 2A, so that's the official due date, then starting into Unit 2B very next. Any last questions at all before we get going back to where we left off? Okay, so let's go back to Unit 2A. We left off all the way over here, example 12. We solved some harder problems in this than the example 12 we're looking, but that's kind of good in a way. This one's a bit of a warm-up problem. We're doing a lot of work with units in chapter 2, and the next unit, Unit 2B, is more work with units, extending on what we know. So let's work with this just as a kind of a warm-up problem and a bit of a refresher. For converting 15 feet to inches, some people are just really, really fast at this. They have really great number sense, and they might just grab a calculator, crank it out, and move on to the next. We're doing all of these step by step just to show how doing the unit analysis works, how to attack these problems on a step-by-step basis, for in particular when the problems get a little bit trickier, like in the next section, just to see how it all goes. So if we're going to do this kind of conversion, we first need a conversion factor, which is 1 foot equals 12 inches. But then from there, we can get started. We can take 15 feet. We'll multiply it by a conversion factor. And what we did in the prior notes was we usually wrote 2 additional fractions based off that one equation. A fraction that had feet in the numerator, and then the reciprocal of it where it had feet in the denominator. But often, once we get some good practice on this, we'll just go right to this step. If we're converting into inches, that means we expect to see inches in the numerator. So from this conversion factor, we'll just write down 12 inches in the numerator. If we place that into the numerator, 1 foot must go into the denominator. And then we know we're on the right track because we get this cancellation here. Feet and feet cancel. The 1 divided into 12 just gives us 12. And all we're going to get is 15 by 12. Let's do a quick check on that. 15 times 12 to get 180 inches altogether. So that's our warm-up problem to get us started for the day. Again, we solved some harder problems already in these notes, but the last 3 examples in this section are building up to more work along these lines, doing these type of conversions. Any questions at all, folks, getting through this very first one for the day? Okay, let's try out another one before we get into the next example. This problem right here is pretty near and dear to my heart. I kind of like this problem because every semester is 16 weeks. So now we're going to ask the question that you might have asked yourself randomly. How many seconds are we actually spending for this entire semester? We're thinking from start to finish, 24-hour days, 7 days a week, and so on. So the amount of time, not necessarily that you're working in the course, but from the start to finish of the entire spring 2026 semester. We need a lot of conversion factors to these, but really we're just doing what we did in part A, multiply by the right conversion factor until we go from weeks all the way into seconds. So if we were to work this out step by step, here's how it would start. 16 weeks. Next, we need a conversion factor that's going to eliminate the weeks. So we might write down something along the lines of 1 week equals 7 days. And let me see if I can write that in a better spot, because I think this fraction gets kind of long. So we'll start off with 1 week. Equals 7 days. Then copying the approach that we took in part A, we need to cancel weeks. So we'll put the 1 week in the denominator from this equation here, and 7 days into the numerator. But our ultimate target is to get to seconds, so we have more factors to get through. And I'll definitely run out of colors, but let's put in a couple just to see the difference. Anyone see what the next conversion equation should look like?
Is it going to be converted, or hours, I mean?
Yeah, absolutely. We got to get rid of days. That's got to cancel. So we could say, just as you said, 1 day equals 24 hours and go from there. So we're going to multiply by this new conversion factor. Days have to be eliminated. So we'll put the 1 day from that equation down into the denominator. 1 day goes here. And 24 hours we can put now into the numerator. We'll abbreviate the unit hours if you like to HR to stand for hours. And then we keep on going. And we're now going from hours to minutes. And by this point, you kind of see the pattern to the process. So to go from hours, we'll say 1 hour equals 60 minutes. I'll abbreviate that one since I ran out of space. So to eliminate the unit hour, just thinking in terms of fraction arithmetic, we'll put 1 hour into the denominator. I'll put HR for the abbreviation of 1 hour. 60 minutes up into the numerator. And you know, at this point, we're just about done. And hey, we didn't run out of colors. So let's multiply next by, well, what are we eliminating? Minutes. So we can say a single minute equals 60 seconds. I'll write the abbreviation SCC for seconds. Then we multiply by, let's see here, to cancel those minutes by the red dot, we need minutes in the denominator. 1 minute times 60 seconds. So we can just crank out this entire multiplication, but the unit analysis side of this, just to double check we're multiplying by the right things, will allow us to see if we're really getting to seconds once we really look into those units. Weeks here's in the numerator, so it cancels with weeks in the denominator here. We have days in the numerator, whether we said plural or singular, day will cancel with day across into that denominator. And then that's just the pattern. We keep canceling from numerator into denominator, the common unit that we see, as if it's a common factor, like on the first problems. But here we stop. Seconds doesn't have anything to cancel into. So we're going to now multiply across 16 times 7 times 24 times 60 times 60 and get an answer finally in seconds. Before we throw all that into the calculator, any questions first with the unit analysis side right here? Okay, let's put this in. We have going left to right 16 times. Here, division by 1 can be ignored. 1 goes into 7 just 7 times. So it's times 7 times 24 times 60. You could put 60 squared here if you like, or just go times 60 again. And here's the figure, 9,676, 800. So that tells us 9 million seconds, 7,600,000 seconds, 800 seconds altogether. So 9,676, 800. So that's the moment the semester started, January 12th at 12 a.m., all the way to when the semester ends. I think that's like May 6th. That's when it'll finally end. This May seconds will have elapsed. Kind of a weird but kind of fun problem as well. Any questions at all running through this one? Okay, I don't know how much of this we've gone through, but we're on week 2. So if we wanted to, we could see how much of the 9.67 million seconds we've gone through, but that would have been a separate kind of question. We have 2 more questions just to finalize these notes before we go to the next unit. And I feel like if I post a problem on here, we definitely have to solve it in class. So let's not ignore these and finish off these last 2. They're similar to the first problem that we started off today, where we have to do some conversions in the middle to get our answer. But the theme for the last 2 examples are we're looking into geometry. Let's hide example 14 first and start off with this one here. The warm-up problem for this new topic is, what is the area in square feet of some 50-yard by 30-yard field? And we know for sure that area is just length times width. If we want to, we could sketch out the diagram for this. We're going about 50 yards. I'll consider this the length. By 30 yards. That's about proportional there for me. Doesn't have to be perfect. So this will be the width. 30 yards. And we can just drop in the information right away and get a value for the area right on this problem. But what makes this problem a little bit more challenging is we also have to do a conversion. We want the answer to be in square feet. So if you're doing a problem in MyLab and it's just not taking your answer, but you know in your heart that the logic is right, you did it right, probably just something like this. They, for no reason in particular, gave us 1 unit, but wanted a different unit in the answer. Well, there's 2 approaches to this. You could do the conversion right here on the dimensions. Then when you go to crank out the area formula, you'll get the answer in square feet like you're expecting. Or you could just crank out the area right now and then take your answer and do the conversion. So either approach is just fine. I'll do it the way the book did for this one. And maybe we could do it in a slightly backwards way where we just convert everything to start on the next example just to compare the approaches. So if we were to just drop all the information into the area formula, we'll say area is length times width. which is going to be 50 yards times 30 yards. 3 by 5 is 15, and then we just carry in those 2 zeros to get that multiplication. And the unit will be in yards squared. Then we have to keep going. Now we need a conversion factor. Based on the work that we just did, we know to get this in square feet, we need to have 1 square yard in the denominator in order to cancel with the yards squared in the numerator. But then the question becomes, what's the value up in the numerator now? And it's a tricky question because we didn't even say what a yard is in feet yet in these notes. Echo says, well, we need to remember or include in our note page these conversions such as feet to yards for exams. I would say no to that question. As far as the exam goes, when I go to write the exams, any kind of strange conversion factor that you might need, I'll have either written into the exam question, imagine this is a problem on the exam, or I'm going to have a table kind of like this one as the last page on the exam, just a bunch of random facts like this. This came from unit 2B, the very next unit, but I felt like it was useful to have pulled up right away. So no, I don't expect you to have memorized a whole bunch of random facts about units. And the problems on the exam are going to be more about if you're given information with the right conversion factor, can you navigate through this and put the answer back into the right units? That'll be the major takeaway of what's being assessed on the exams. Any other questions at the moment? Yeah, absolutely. Thanks for asking about that.
I do have a quick question on what you're doing right there on the problem part. You have a question mark over 1 yard squared, but you
Yeah.
haven't multiplied. Would it be divided because we're going to go from a larger to like I don't know how to, in my mind, I feel like I should divide. Does that make sense?
It kind of does, but the division should be just the yard squared to the denominator, because we have to cancel this yard squared right here and end up with some, oh, didn't mean to do that, end up with some quantity of feet
Feet there.
squared for square feet in the numerator. So it's going to be kind of like how we went from, in this problem, feet into inches. We had to cancel the feet. Imagine that's the yard in our current problem, by having 1 foot in the denominator there, and then some quantity of inches up in the numerator here. So it's going to be kind of similar to these where it's a multiplication.
Okay,
Does that
I
make
understand. Yeah,
sense?
I don't, I was thinking division, but for some reason I was thinking I had to divide.
Gotcha. Other questions or comments so far? Okay. Probably a lot of people know how a yard converts into feet. And like I mentioned, or like the question was asked before, if this was a real exam question, this information would be put on the exam as well, possibly through, say, this table, where it just directly says 1 yard is 3 feet. If you're doing this problem on, say, MyLab, they often give you a link to pull up a table just like this. But sometimes it's not a bad idea to just open up a browser and just say yards to feet, and it just gives you directly a pretty fast unit conversion. So sometimes that's just the most convenient way to go, depending on how you like to look this up. So either way we take a look into it, 1 yard will equate to 3 feet. Let's put this up above. 1 yard equals 3 feet. That means where the question mark was, we just need to fill in 3 feet altogether. So now we're ready to start canceling. Yard squared here will cancel with these yard squareds. The answer is now in feet squared. So 15 times 3 gets us to 45. Then 0, 0, feet squared. So now we have the answer back into feet squared. Well, any questions at all with this one? It has a lot more noise going on because now it's an area problem, then a conversion. Okay, and again, just as we mentioned before, there's multiple approaches to this. Some people might have felt like doing the conversion once we got the answer in yards squared was kind of weird. So if you wanted to, you could just convert this into feet if you prefer and go from there. Just to see how that goes, let's take a look at that just in this problem. Let's say we attack this in an entirely different way. So same figure before. We're trying to get 4,500 feet squared, and this conversion factor still will work for us. So another perfectly equivalent way to solve this, not the way the book did it, but you don't have to do it, hang on, exactly the way the book did it. I'm noticing there is a mistake, however. Maybe before we do this one, there is a mistake in that answer of 4,500 feet squared. Kind of a surprising mistake that I wrote that down, but you know, it's easy to make mistakes with these. Anyone happen to see what the error is in this conversion factor? Again, it's kind of a subtle one. Maybe it's a good thing this mistake happened because now it becomes do not do this kind of a problem. Just as a paper trail in the notes, let's put here a quick revision just as a reminder. It's not actually 3 feet at all. Exactly. Thanks for mentioning that, Echo. My mistake was the conversion factor is right, but we want feet squared and yards squared in our conversion factor, and that's not conveyed here. So both sides of this equation should be squared to get the right factor. I'm going to leave the slash mark here just as a reminder. And this is what we'll do very next. Let's take 1 yard, square that so we can get yard squared. Take 3 feet, square that one so we can get feet squared. When we square this one, we get a 1 times 1, so still 1. But the unit now becomes yards squared altogether. Here on the right-hand side, we have to take 3 times 3 to square that value. So we get to 9 feet squared. And that's the mistake I made right here. So let me just erase this in full so there's not a whole bunch of weird slash marks on these notes. It's not going to be a 3, it should be a 9 altogether. So don't forget this step right here. It's all about the actual dimension of the units. It's in yards squared, so we had to have feet squared in the actual conversion factor we're using. Might as well just highlight all of that to convey why it's a 9. And at this point, I feel like I'd rather grab a calculator for this one. Let's multiply 1,500 times 9 to get 13,500 square feet is the area of this region with that correct unit. Okay, that's a good correction to put in. If we try this in a different method, I put a little border here just to say you don't have to do this twice, but here's going to be our method 2 next. We were definitely not going to get the same answer without that correction. Okay, maybe method 2 might seem a little bit more simpler after having to navigate through this. I think the book likes to go this approach just so they can discuss that strategy right here of squaring your conversion equation to get the right conversion factor at this step. But a totally fine way to attack this, like we mentioned, is put both the width and the length in terms of feet just to start it out, and then run it through the area formula. So if we read the problem through this way, we would want to put 1 yard in the denominator, 3 feet in the numerator. Now the 3 feet is correct because the dimensions are to power 1, just yards, not yards squared. We have the right cancellation, and we get the width is 90 feet. Let's do the same cancellation down here for the length. Length is 50 yards to start. Multiply by 3 feet per the 1 yard. We canceled then, just as before. And now we have that the length is 150 feet. From those 2 units, if we multiply them together, we should be getting 13,500 feet squared. So the area is going to be length times width. Now in the right unit, it's 90 feet. Let me erase that parenthesis. It's going to be 90 feet multiplied by 150 feet. Just like up on top here, we're taking feet times feet. It just looks different. This is feet squared. Down here, feet times feet is also feet squared. Now here's the moment of truth. We're going to take 90 times 150, and we get the same value out, 13,500. Looks like a kind of a cleaner solution. We did have to convert two different quantities. But I think this error is a little bit easy to sneak by, so this feels like a cleaner and maybe a slightly safer approach as well. Well, this is the problem done a couple different ways. Any questions at all, folks? Getting through the formula and doing the conversions? Okay, let's get into the last problem in the notes. Then we'll convert over to the section units 2b. Keep saying section, I'll get that down eventually. This one is, in essence, the same sort of problem, except this time it's a volume problem, so one extra dimension to take into account. We're told we're building a new sidewalk, maybe something around University Place or the Pocatello campus. It's going to be 4 feet wide, 300 feet long. And I don't know if this is good for Idaho, but we're filling the depth of this sidewalk at a depth of 8 inches of concrete. And there's 3 kinds of units here. This is kind of annoying. We have dimensions in feet for length and width. We have inches for the depth. I mean, that makes sense if we're not going to go a full foot to say it's in 8 inches. But maybe the contracting company likes to sell concrete by the yard. We need to know how many cubic yards of concrete, the volume in other words, that will be needed to actually create this sidewalk. So we're going for our answer, an expression in yards cubed. There's lots going on since we have an extra dimension, so let's draw this out just to organize all of the information in the problem. It's not going to be the world's best sketch, but it'll do the job. So here's my attempt to say, here's the width of 4 feet. This is not to scale, but it'll convey the information. This is the length at 300 feet. So width equals 4 feet. Length equals 300 feet. So we have the dimensions from the first sentence, and we have a fill depth of 8 inches. Well, I made a 2-dimensional object, so I'm just going to say depth. Instead of drawing it in, let's just add a statement. Depth will be 8 inches altogether. We're going for a target of cubic yards. And now the formula that we're going to be working in this problem is that volume is going to be the length times the width. And we often say height in the volume formula, but if we wrote it in as depth, no harm in saying it this way, length times width times the depth, playing the role for height. Okay, that's the organization of the problem. And just like on example 13, there's lots of different ways to do this. What we don't want to do is multiply these 3 dimensions all together because there's a unit mismatch. We also want to make sure we convert into cubic yards. So maybe one approach is convert this into feet, multiply all dimensions together, then do a final conversion back into cubic yards. Or we could convert every single dimension we see here into yards. Then we can just multiply all 3 together through this formula. Well, there's lots of ways to start. Anyone have a preferred way to go? This one can be our choose our own adventure kind of a problem. Should we convert everything now or just do the conversion at the end step?
Maybe convert it at the end.
Okay, let's go for that approach. So first, let's get our volume. We're going to take length times width times the depth. That does need one conversion. So we're going to do one tiny conversion in the middle, and then get an answer in cubic feet, which we'll take back to cubic yards. So let's start off by saying the depth of 8 inches Let's just write it down as a variable d, so it looks like an object we're dropping in the formula. So depth by that variable of 8 inches. We'll use the factor that 1 foot equals 12 inches. This time we want to eliminate the inches and get it into feet. So we'll put 12 inches into the denominator. Now we can cancel across the numerator into that denominator. We'll have 1 foot in the numerator. And here's our cancellation. Now it's a bona fide fraction, but we could take 8, multiply it to 1 across the numerator, get 8 divided by 12 feet. And if you left it just like that, no harm done, but this is one part of a larger problem. So if we reduce it, it could make our work a little bit easier down the line. So let's also reduce the fraction. 4 goes into 8 twice, into 12 3 times. And so this is 2/3 of a foot. So we've got a depth. Now we can use these 3 different units and say volume is length times width times depth. Let's go down the line, cite those values. First, we have a length of 300 feet. In place of the width, we grab this value, 4 feet. Then we'll multiply all of that by the depth of 2/3 of a foot. So parentheses here just to indicate multiplication. And this is a statement that will reduce as well. We can divide 3 into itself, getting a 1. Divide 3 across the factor in the middle all the way here to get 100. And now we're taking 100 times 4, so 400 times 2 for a value of 800 altogether. And it's feet times feet times feet, so it's 800 cubic feet. We have the right volume. Now all we need to do is convert it into cubic yards. Well, we're mostly done with the problem. I think this is the major thing we needed to have a diagram to organize the information. With that conversion in the middle was kind of unexpected. Any questions at all, folks, getting that value so far? Okay, let's go for the conversion factor.
I'm sorry, it was a little slow. So when you're reducing across and you have more than one, like more than 2 variables, so you have the 3 variables, you only have to be able to divide one of those to reduce. Like I don't need to be able to divide the 3 into the 4.
Yeah, that's correct. It's true as long as you're multiplying right across here. So if it was a plus and a minus or a minus between, then yeah, the 3 would have had to divide both. So just
Okay.
a quick example to go along with that. That's a great review problem to go along with this one as well. So if you have something like, say, 3 times 4 times 2, divide by 3. I arranged it a little bit different, putting all numbers into a numerator and that 1 3 into a denominator. But in this kind of arrangement, the 3's would cancel and you would get just an 8. But the one we have to be really careful with is, what if you had 3 plus 4 minus 2 divide by 3? Well, you know you can still cancel this 3, but what you're really doing is taking this 3 and dividing it into everything. Pluses and minuses make algebra just a little bit more challenging. This becomes 3 over 3 plus 4 over 3 minus 2 over 3, which it becomes kind of a more inconvenient expression. Sure, we got one cancellation, but everything across a plus and a minus has to also be divided by 3 as well. The multiplications are the nice one. You only have to cancel in one spot, just like that, and then you're all set. Other questions at the moment? Okay, well, let's do this conversion factor. Let's go for maybe a different color this time. We're trying to get into cubic feet, but we learned that 1 yard, excuse me, I said that weird. We're trying to go from cubic feet into cubic yards, and we know that 1 yard is 3 feet. then in view of the mistake that was made in just the last problem in the notes, we can't use this factor because we have feet cubed. So we just take this and raise both sides to power 3 to get the right unit. Now we have 1 cubic yard is equal to 3 times 3 times 3, so 27 cubic feet. Now that's the actual conversion factor we'll use. Volume, which is 800 feet cubed, will then become multiplied by, before we write down the fraction, always think, what are you trying to eliminate? We're eliminating the cubic feet, so we'll put 27 feet cubed. Coming from this conversion factor, or really an equation right here. We end up with 1 cubic yard in the numerator, but that matches with our goal. That's what we want the unit to turn into. So the cancellation goes this way and this way. And I noticed on this problem, I forgot to say what to round to. Sorry about that. I think the typical thing that would have been stated on the actual MyLab exercises would have been round to the nearest. Ten, or round to 1 decimal place. Let's put that in just to make this more similar to what a MyLab problem would look like. Then back in the calculator, we'll go 800 divide by 27. Then to the nearest tenth, this one will round down to a 29.6. So volume of concrete that has to be poured will be 29.6 cubic yards. Let me double check the number on that. Okay. Well, we did it, folks. That's the completion of this example here. Any last questions on getting through that example 14? That was a lot of examples now that I reflect on that. Okay, well, let's save this up. Our next goal is to move now into the next unit. We spent a good amount of time on units 2A. 2B and 2C are going to be shorter units altogether. And 2B just seems to be continuing on really the theme that we've been working on all along in 2A, extending unit analysis. It starts off with a kind of a random topic. Doing these interesting arithmetic operations. The reason we're going to be doing these kind of problems here is part of extending unit analysis is now going to be working with different kinds of units, say these sort of conversions that we have here. Later on, if we scroll through the notes, we're going to be working with these kinds of units as well. We're going to be dealing with, say, millimeters, micrometers, nanometers, and so on. Or to change the units, we might be working with watts or kilobytes. So we might be working with, say, megabytes, gigabytes, terabytes, and so on. And these all involve powers of 10 as they come up. This is a shorter section, like I mentioned, but I felt like just getting some practice working with powers of 10 is a good idea for this section. Just like I mentioned for the prior sections, the order of the notes that you see here also mirrors the order of the problems that you're going to see on the MyLab homework. So in Unit 2B, this is about the types of problems you're going to start off with. We're going to do some multiplications, divisions, and such. But the trick for this one is we want to express all of our answers as a power of 10 for example 1. Example 2, we're going to write either an integer number or a decimal number. So there's actually lots going on with these kind of problems. We'll take our time with these. Really, the side goal that's not really mentioned here that we'll be doing at the same exact time is we're going to be practicing exponents. Or in other words, practicing exponent, said this in a weird way, practicing exponential laws. So let's give this a try. going down the line, we can do these pretty fast because, I mean, we can just throw these into a calculator if we were so inclined. Not necessarily the best strategy, but good to visualize what it would look like. If we really wanted to, we could go 10 to the power 4, multiply by 10 to the power 2, and get an answer like that. This is going to come out as 1 million. And you could write this out as a power of 10. That should be 10 power 6. But a nicer way to go is just practicing the exponential laws. And this is the law that's relevant to this one. If you have anything along the lines of a to the power of m times a to the power of n, the result is going to be a to the power of m plus n. Really, we've kind of seen this before. We took feet times feet. Those are things to power 1, and when we multiply them together, we got feet squared. In this particular problem, 10 is going to play the role of a, the base. M and n are going to be exponents 4 and 2. So this just becomes 10 to the power 4 plus 2. And that's the main punchline with this problem. We take the exponents in this configuration, just add them together, and the answer becomes 10 to the power of 6 altogether. So that's the work we're going to be practicing in this section just to start it out. We'll move back into this when we start looking into things like nanograms or kilometers. Kilometers is usually the way we say it. So this will serve its purpose later on in the notes. Any questions with the first problem here? Okay, let's take a close look on this one. Pause for just a moment. Give this part B a try and view on what you did in part A. This one really doesn't have a law step, so let's just give this a moment to look at it, think about it, and the property here. And if you come up with the answer, don't hesitate to say it in chat or through voice. So give this a try and let me know the moment you spot a candidate value for this one. Yeah, absolutely, Amy. This one just becomes 10 to the power 3. Good call. It feels weird because now we're dealing with a negative exponent on this one. Sorry, I lost control of the scroll. There we go. But the exponent property that we stated above here is still relevant. It's kind of a nice property in the sense that it actually doesn't matter what kind of number m is. It could be positive or negative. It could be an integer, a decimal number, a fraction. The property works exactly in this way. So if you have 10 to the power of 7, power negative 4, we still add up the exponents, but we're taking 10 plus a negative 4 really. So this becomes 10. Let me actually go down. This becomes 10 to the power of 7 minus 4. So altogether, this is 10 to the power of 3. 10 to the power of 3 works out to 1,000. So if you had to do this problem and you wanted to double check, you could just write out in this way. 10 to the power 7 times 10 to the power of negative 4, as weird as it looks. Yeah, it does indeed come out as 1,000. So there's no harm done in doing an independent check like this to see if your logic is on the right track. We're writing it out in this way as a power of 10. So that's why we left it in that form rather than saying 1,000. So that's the name of the game of these problems so far. This one is suddenly quite a bit different. There are different kinds of strategies for working a problem like this one. But I think the standard way people would typically think about this is just a different exponent law. So if you're not multiplying, but instead you're dividing, the new law becomes a to the power of m divided by a to the power of n becomes a to the power of, it's subtraction this time, m minus n, which seems kind of weird in a certain sense. But maybe it seems about right. the inverse operation for multiplication should be division. So the inverse operation, the formula, the result you get for addition should be subtraction. So that's one way to convey the logic on this one. That means this problem is just as fast, really. The result on this one will be 10 to the power of 15 minus 5, which will give us 10 to the power of 10. You might know from experience, 10 to the power of 6 would give us a million. 10 to the power of 9 would give us a billion. So this number is 10 billion at 10 to the power of 10. But this is the answer that we want to express for this one. You know, there's more than one way to think about this. So if you've done some work on exponents and you aren't a big fan of seeing it this way, there's other ways to visualize it. But any questions on getting that answer so far, going that route? Oh, that's a great question too. And again, yeah, it seems weird. We're dividing here, but the answer wouldn't be 10 power 3. We do a subtraction as opposed to a division, which feels weird because we are literally dividing when you read the problem. So here's the logic that connects with that question there. Let's solve this one in a separate way to see how that connects with that question. If you do 10 to the power 15, divide by 10 to the power 5, here's another way to visualize this one altogether. It's really a matter of seeing what happened in part A, but going backwards. If you went backwards, you could take something like 10 power of 6 and rewrite it as 10 power 4 times 10 power 2 if you decide to go backwards. Likewise, down here, you could split apart 10 to the power 15. We typically say we're factoring it. You could rewrite it as 10 to the power of 5 times 10 to the power of 10. That works out because in this configuration with a multiplication, you just add those two exponents and you come back up to 10 power 15. But then notice when I copy in that denominator, 10 power 5 across, now we're going back to our work with fraction arithmetic. We have a like factor in numerator and denominator, so we can cancel this 10 power 5. We can cancel that 10 power 5 across top and bottom, and we're left with 10 to the power of 10, like in this version over here. So the formula is nice, but it's confusing. It's really just a shorthand of what you're really doing right over here. So this is another way to visualize it. Any questions seeing it this way as opposed to that version there?
I have a question that, so we're doing to the power of 10. Will it always be a 10 in the top and a 10 in the bottom? Like what if it's a 10 in the top and an 8 in the bottom?
Oh yeah, that one would get a lot bit different, and it would take a lot of work to get that into a base of 10. We might have to get into logarithms, which will be later on in the course. But for these problems, it's always going to be powers of 10, both top and bottom, that we're going to work to really make sense of these instructions. And
So
the
we'll
reason
never
it's
have to worry about them being two different numbers that we have to.
yeah,
Okay.
yeah, that's correct. That would be pretty rough. That would take a little bit more ingenuity here. And yeah, the reason we're doing just those problems with powers of 10 is because we're thinking of just going back to this part right here, where we have powers of 10 for each of these different kinds of units, deci, centi, milli, say millimeter, for example, versus deca, hecto, kilo, mega, giga. All these are just different powers of 10. So we're just in that really narrow topic there. Other questions so far? Okay, let's try this out again. This one's kind of nasty in a way. I mean, it fulfills a theme, right? When we did part A, values are positive, and then when we did part B, we threw a negative value in there. And we observed the formula works in the same exact way. And the formula down here also works in the same exact way, but this is a pretty tricky kind of problem. Really, there's really two major approaches you might take. You might use this formula right here, It still works, but now we have double negation, so we have to be careful. But another formula says, if you have 1 over a to the power of negative n, this converts to a to the power of a positive n, but no longer in the denominator. And it goes both ways. A different version of this formula is a to the power of negative n. If you want to remove that negative sign, you could put the base a into the denominator, and now it has a positive exponent. So this is one way to go. There's two main approaches. Either use this formula here, or use either this formula or this formula and force our exponents to be negative. Let's practice it both ways just to see how either approach is going to work. By the way, one way to memorize this new pair of two formulas that we just put down is you can force a positive exponent just by switching position from denominator up to the numerator. Or if it started negative in the numerator, just throw it into the denominator. Exponent is now forced to be positive. But to make sense of that, let's work this problem carefully. First, let's go with this approach, where the red dot is using that formula. We have a power 6 here and a power negative 3 here. The major thing about this formula is there's always a negative sign in the middle, no matter what the value m or n happened to be, positive or negative. So if we did it this way, we would get 10 to the power of 6 would go here from the numerator power 6. There's a minus in the formula as well. So connecting the yellow, here's us putting in the negative signs. And then the last thing, the value for n in our problem is negative 3. So we would put a negative 3 right here, copying in that formula just as we see it. Again, that's pretty weird, right? This is 10 to the power of 6 minus a negative 3. Law of signs now say the negative of negative 3 is positive. So this is the 10 to the power of 6 plus 3, which gets us to 10 to the power of 9. So that's one way to do it. Any questions going this way, just directly using this formula? Okay, let's see it a different way, just for the sake of some clarity on this, because it, again, is kind of a weird formula when you use this, and suddenly you have extra negative values that are showing up. So a second approach on this one, it's called as method 2. If we have 10 to the power of 6, and we're dividing it by 10 to the power of negative 3, sometimes a clean way to approach this is just make the exponents friendlier. Negative exponents are the foggy, vague ones, so it makes more sense if you force that to be positive. That means you're using this formula right here. So we already have a positive 10 power 6 in the numerator. Let's copy in 10 power 6, no change on that one. But then we're going to multiply by changing that one from a position denominator up into numerator, much like this formula here is conveying, going from denominator up to numerator. This would then become 10 to the power of now a positive 3. So the negative n becomes a positive n. Same idea there. And now we're back to part A. Now we're just adding the exponents. Power 6 plus power 3 takes us to 10 to the power of 9 altogether. So that's a landscape of what can come up on these notes. As the questions we're asked about so far, there's other things that can come up, but this is the view of what we're going to see in section unit 2B rather. So here's the whole landscape of the things we've practiced so far. Any questions on getting through any one of these computations, A through D? Okay. Well, aside from these exponent laws that we looked into to get through these kinds of conversions, other things we might want to do is just say, what is the numerical value? If we're mixing different powers of 10 and Instead of multiplying or dividing, say we're adding and subtracting those values. The instruction switches on this one. It says, in my lab for these exercises, our goal is to write down either an integer value or something that involves a decimal as well. New exponent laws are going to come up as well, but now this is more just crank this out and get a number that's not a power of 10 any longer. So instead of writing 10 power 9 on example 2, we would have written 1 billion, 1 with 9 zeros. But I think this one is kind of a friendlier problem to start off. 10 squared is really just 10 times 10, so we get a value of 100 on this one. But this one is kind of the weird one, 10 power 1. It just looks funny, but if you saw 10 power 1, any volunteers to say what that number would become?
Would it just be 10?
Yeah, exactly. Any number to the power of 1 is just that number itself. So we would have 100 plus 10, and the whole answer to this one would just be 110. When they say to write an integer, that's what we mean right here, some whole number that could have been positive or negative. We're done with this one, but the exponent law that's working for us in the background is that a to the power of 1 is just itself, a base a. So much like 10 power 1 came out as a 10 on this example. It does get weirder though, notice. 10 power 0 is a pretty weird statement to write down. So here's the next one we need an exponent law for. Oh, sorry for missing the chat on that one. Yeah, absolutely, Echo. That one comes out as exactly a 10. How about for this one? This one is, I feel like, the weirdest thing we put down on paper so far. Anyone happen to know what something to a power of 0 would come out as?
Would it just be 0?
Turns out this one's not 0. It's kind of a weird one altogether. Here's one thought, though, as a kind of a hint on this one. A great question is, why is it not 0? Well, think about how something to a power of 0 might come into play in a particular situation. If you use our exponent laws that we've been discussing so far, let me just restate one for easy reference. If you take a power of n, m, divided by a power n, it's a subtraction problem. The numerator exponent minus the denominator exponent. Yeah, good call. It is absolutely a 1 on this one. It turns out anything to a power 1, to a power of 0 would come out to a 1 exactly. And the quick example that goes along that is, suppose you use the exponent law right here by the red dot, but your problem was 10 squared divided by 10 squared. We know that's 1 because the same number divided by the same number is a 1, so we knew that to start. But what about the exponent law? I mentioned that it works for any value of m and n, and it will also work if both m and n are the same value. You would get 10 to the power of 2 minus 2, which would give us 10 to the power of 0, which looks funny. And then we might say, well, what is that? Well, equalities are special. It's like a track of logic that takes us all the way to the left. And we could say, well, we do know 10 squared is 100, divided by 100 again is 1. Connecting those together gives us the exponent law. That law is a to the power of 1 is just a, and now a to the power of 0 comes out as a 1 altogether. It's kind of strange in a certain sense. We force that to work because we want this formula to always make sense. And 10 squared divided by 10 squared is a 1, alternatively written as 10 power 0 if we use the exponent law. So again, these are some pretty strange concepts altogether. Does that make sense to folks on why we should get a 1 right here? Okay, another reminder is that our course for exams is Open Calculator. You're expected to be using your calculator as well as you're doing the homework problems or the quiz problems. And there's no harm just double checking this on a calculator. So grab your favorite calculator, input 10 power 0. That's a great way to just double check this kind of stuff. Any questions at all putting it into the calculator or running it through like this? Okay, and by the way, if you ever do have a pertinent calculator question, don't hesitate to ask. I'll be very happy to help out. I feel like exponents are the first thing where putting things into the calculator can get a little bit tricky. So just for a quick look into that, let's pull up a calculator. My go-to is usually something like the TI-30X2S is a pretty great calculator for this class. It's a basic scientific calculator we can put in lots of stuff in one line. So now if you wanted to put in 10 to the power of 0, here's what it would look like. Let's just pretend this is a real calculator for the moment. Here's our calculator. I need to fix this a little bit. Now let's just pretend I have a model with a completely black screen. If I want to verify this in a calculator, I mean, we show it in Desmos, but you'll notice my Desmos calculator feels a lot different than the one you'd be using in an exam setting. So the thing you would want to hit is first, just type in 10. It'll look about like this on your calculator. And the big button that we would want to hit for this context is going to be this one right here. This one gives us the exponent. When you type that in, it prints like this, 10 to the power of 3, or hang on, forgot what we were doing, 0. Hit enter, and you should see a 1 pop out in that calculator. So let's go back to the original problem, part B. Looking at 10 power 0, there's lots of ways to think about that one. But either way we visualize this, we get a power 1 altogether. We knew 10 squared was 100, but really all we're doing is taking 1 in place, putting in 2 zeros, much like what Echo is saying. This is 1, but with 0 zeros is a great way to think about that. Here, 10 to the power 4 is going to be a 1 with 4 zeros. 1, 2, 3, 4, so 10,000. So that means altogether, 10 to the power of 0 plus 10 to the power of 4 comes out as 10,000 and 1. Let me put a box here since there's extra stuff down below. But we got it, folks. This is something you could have put into the calculator just in one line, but it's good to see what's happening with those exponents as well to help out with later on in the notes. Any questions whatsoever finishing this one? Okay, so last one on the table is 10 to the power 30 divided by 10 to the power of 33. Well, this one is another one of those problems where we could use the rule a power of m divided by a power of n is a to the power of m minus n. But that one's going to come out weird, right? If you did that, you would have 30 minus 33, and that would have came out as a power of negative 3. But the cool thing about this formula is there's two ways to write it. You could also say a to the power of m divided by a to the power of n is 1 over a to the power of n minus m. You can just subtract differently. You could take the 33 minus the 30 and just leave 1 over 10 power 3 in the denominator of this one. So there's lots of ways to attack this kind of problem. And really, at the same exact time, you could just say that this is 10 to the power 30 in the numerator, but a whole new different approach is just factor that one. This is the same as 10 to the power 30 times 10 to the power 3. And now we can do a cancellation going this way and this way, leaving a 1 in the numerator. And we get 1 over 10 to the power 3 as a result on this one. We can't input this answer because we need either an integer or a decimal number. And this is the one that's going to turn into a decimal. The thought with this is if you're dividing 1 by a power of 10, you start with a 0, and we're going to put in 3 decimal places, 2 decimal places, and then a 1. And then this would be the answer on this one. In other words, this is 1 over 1,000, so we write in as 1,000th in this way. And memorizing a whole bunch of different exponent laws isn't meant to be something that becomes a big burden in these notes. If you decide to view it this way, 10 power 30 divide by 10 power 33, that would be okay for this course as well. We're seeing how it works as an exponent as well, just in case 1 over 10 power 3 comes up. But if you just crank this out into the calculator to get the decimal number, that would have been okay getting through this one. Well, we did it, folks. That's our run through with dealing with powers of 10, really just a way to also think about exponential notation and exponent laws. Any questions with that quick crash course getting through these? Okay, well, with what we're going to be doing later on in the notes is now returning to the topic that we left on, Unit 2A. We're just doing more unit analysis, but this is an extension of what we've seen already before. Information like what we see here are going to come into play. Issues with lengths, weights, and volumes. Some of these units are kind of weird. For example, I never knew the unit 1 rod is 5.5 yards. That's a brand new one for me. Other things that I probably have heard before, but I never really knew are things like nautical miles and leagues, and furlongs are weird things. So we're going to practice these kinds of units. Then later on, we'll also work with the system here, things along the lines of decimal, centile, micro, and so on to do other conversions. I'll end on things along the lines of population densities on example 8. So this will be a shorter set of notes. We'll probably finish this one off when we come back next class. But I think this is probably a good stopping point for us. I don't want to launch into a whole new problem in less than 3 minutes of time. So any final questions before we call it a night today? Okay, well, have a great night, folks. Thanks for your active participation, attendance, and getting through the notes. We'll be through this course in no time. It's something along the lines of 9.5 million seconds for a 16-week semester, but we're nearly done with week 2, so we're on our way. Have a great night, folks. Thanks.